our next team is our 3D shape modeling. So if the 3D shape modelers can come up. Again, we'll have our same review panel for this. But I just, whilst the team's getting set up, just wanted a quick shout out to Peter Janeskins and Sidhu Genju, who are amazing supporting our Comets team. And of course, probably very proud somewhere in the audience. But I don't know if you guys are there, if you want to quickly stand up. And, yeah, there. So, with that, are you guys good to go? All right.
Okay, so hello, we are the team that has been working on 3D shape modeling of near-Earth asteroids using radar data. So let's briefly introduce ourselves. I'm Sean Marshall. I'm a grad student in Cornell Astronomy working on observations of near-Earth asteroids.
Hi, I'm Adam. I'm a PhD student at the University of Oxford and I'm studying machine learning.
Hi, I'm Grace. I'm also a PhD student at Oxford. I study ocean engineering.
And my name's Agata Rożek, and I am a planetary scientist at the University of Kent. And we would also like to we would also like to thank our mentors, Michael Bush, who is an astronomer at the SETI Institute, and Shadi Raisi, who is the senior researcher at INRIA in France. And we were also supported by Yarin Gal and a member of the AI team, Justin. So,
all right, so asteroids. Here's a plot showing near-Earth asteroids in the inner solar system as of yesterday morning when this plot was generated. So there's thousands and thousands of them. All the red dots on this chart are those that come close enough to be considered near-Earth asteroids, close at some point in their orbit, although right now, some of them are out in the asteroid belt. So the blue ellipse is Earth's orbit for scale. Anyway, red ones are near-Earth asteroids, NEAs, green dots are other asteroids. So there are about 16,000 known near-Earth asteroids, and for most of them we only have fairly limited information on the physical properties. Usually just a rough estimate of the size, and that's about it for the vast majority of them. And there are about 30 new ones discovered every week, so the characterization lags well behind the discovery. And physical properties, however, are very important. Scientifically, they're important for understanding the solar system's origins and evolution. Also, knowing the physical properties of an asteroid is very important if you ever want to send a spacecraft mission there. Physical properties are also critical for planning deflection of potential impactors if we ever need to do that. So the best way to characterize near-Earth asteroid, or anything really, is to send a spacecraft there. However, spacecraft missions are fairly rare, fairly expensive, and unfortunately I don't think it'll be anytime soon that we're able to send out 30 new spacecraft per week. So if you're working with observations from Earth, just about the best you can do for characterizing asteroids is using planetary radar. So radar observations are different from most of astronomy in that for most types of observations in astronomy, basically whatever light comes in, whatever photons come into your telescope, that's what you get and that's what you're stuck with. You have no way of just saying, like, make the object bright, or you need to wait longer, or if that's not practical, find some other way to do the study. But radar is different because we transmit the signal that goes out, which means that the observer has flexibility in choosing the time structure and the polarization in such a way that we'll get as much useful physical information back as possible. So we transmit the signal, it goes out at the speed of light, and then we get the echoes sometime later, typically a few minutes. So right now there are 2 active planetary radar facilities in the world, shown here. This is Arecibo in Puerto Rico, 300 meter diameter. This is the transmitter on the Goldstone DSS-14 antenna in the Mojave Desert. These are shown in the same proportions. There's a scale bar. And both these planetary radar facilities are funded by NASA. So here's the plot of radar observations over time. At this point, over 700 near-Earth asteroids have been observed by radar. The observations have really picked up in the past few years as NASA put more funding into planetary radar programs. So now we're observing close to 100 every year. So again, that's only a small subset of the total number of known near-Earth asteroids, but even so, we're observing them at this point faster than we can analyze them in detail. So here's an illustration showing what kind of information we can get back from the radar observations. This is a simulation of asteroid 1999 KW4, which is a walnut-shaped primary with a small satellite going around it. So on the right here, this is the plane of sky view. So this is what you would see with your eyes if you were floating in space near the asteroid. And on the left here is the delay Doppler image. So we transmit the signal. It gets dispersed in frequency because different parts of the asteroid are rotating toward or away from the observer. It also gets dispersed in time because the parts, you get the reflection first from the part of the asteroid that's closest to the observer. So call these delay Doppler images. Delay is on the vertical axis here, so stuff on the top is closer to the observer. So right now you see the satellites coming back around. Here the satellite's closer to the observer. Now it starts to move away. Our horizontal axis is frequency, so on the right is stuff that's rotating toward the observer. Left is moving away. So again, satellite goes down behind the primary, you can't see it, so it comes back around, now it's moving toward the observer. So these radar images can be somewhat misleading in that they are very different from what your eye would see. It's a different sort of projection, and but still they're images. So we want to be able to use these and do the inverse problem, figure out the shape and rotation state of the asteroid that would give us the images that we observe. So here's the pipeline of how we do shape modeling. The software that we use to get the shapes is simply called Shape, easy to remember. Anyway, so several steps here. So first off, we have whatever set of observations. Need to do pre-processing, get all the data into a format that the shape software understands and can work with. That typically takes a few days or maybe up to a week, depending on the observations. So basically we have to start with simple models and then work our way up. So often start with something simple like an ellipsoid or a pair of ellipsoids in this case, gradually refine the shape, figure it out in more detail. And one important part of modeling is finding the spin state of the asteroid. So in particular, the pole direction we call it. So which direction on the sky does the asteroid's north pole, does its rotation axis point to? This is often a very tedious process, can take hundreds or 1,000 calls to shape, but eventually we narrow it down, refine the shape, go into more and more detail, and for the final shape models, there's typically, represent them as a triangular mesh with 1,000 or 2,000 vertices, vary the positions of all those vertices. That means over 1,000 free parameters, but eventually get back a nice detailed shape model. So this is great, but it can be a very time-consuming process, takes a lot of computational time. It also takes a lot of time for the human who's looking at this and trying to steer the software in the right direction. So we want to speed this up any way we can. So for this summer, continuing on the work they did from FDL last year with shape modeling, we've identified several stages of this process that we want to focus on and try to speed up. So Grace will talk about.
All right, I'm going to get started talking about some of the solutions that we've developed in the last 7 weeks. One thing we've done is make one step of the pre-processing of data faster. So when an astronomer has these original delayed Doppler images, they need to, by hand, find the signal inside the noise. We've automated that process using a density-based clustering algorithm called dbScan. That might sound familiar because the Comets team also uses this algorithm. dbScan is in a script that we put together that automatically finds the signal in these images and returns the masked images. So these masked images can go straight into the shape modeling process. Here's just another example of that working on a different type of signal. We've tested the script on over 700 images, and it's worked on all of them. It even works on binary systems. It correctly finds separate masks for the primary and the satellite. Now, we're also able to mask the millions of synthetic delayed Doppler images that we're generating to train our neural network. This process, Agatha and Adam will talk about later. But when we're masking the synthetic images, like these here, this example is synthetic images, it's not of a real asteroid. These, we don't use density-based clustering because it'd be too time intensive. Instead, we know exactly where the signal is, and we're masking based on that. Now, by picking out the signal from the noise, we can determine the bandwidth of a signal, and because we know the time steps between each set of images, we can guess the period and diameter of an asteroid just from the delayed Doppler images. And this is useful because in some cases you might not have that information, the period and the size from, say, the light curves. So if we can guess those just from the delayed Doppler images, then we can start running the shape modeling process faster with better starting points. All right, now I'm going to pass it on to Adam.
Thanks. So I'm going to be talking about how we probably need this. I'm going to be talking about determining the spin axes for asteroids, because this is a really important part that we need to know in order to model the shapes, and it can take lots of time to find it. So by spin axes, we've just shown a bit of a diagram here. We're looking for the beta and lambda, and this is corresponding to the longitude and latitude. Now, what normally happens with trying to find the spin axes, we do a grid search on a sphere, pass it into Shape, which is this software that Sean spoke about, and this is really expensive. And doing a grid search can take a long time, maybe I think to start with, maybe about 400 calls to Shape or something like that, and then going finer and finer, lots of intensive time spent looking for this. So and there's some more information about that. So what we did is we decided to use something called Bayesian optimization to more intelligently select some of these spin axes combinations. And just to give a brief overview of what this is, the idea, this is in one dimension, is to select areas that we are confident that we're going to do well in, a low chi-squared or mean squared error, or pick areas that we're not sure about and we might do well there if we haven't looked there before. So that's kind of the idea, rather than doing this grid search. So this is an example. So last year, the FDL team did Bayesian optimization, but what they did is they were measuring distance on a plane. But we know that the distance is really, we should be doing this on a sphere. So you can see here that we had some problems where the Bayesian optimization thought that the south pole was a line and the north pole was a line, and 0 degrees in longitude was the same as 360 degrees in longitude. So what we wanted to do is we wanted to do Bayesian optimization on a sphere. So we measured distance on a sphere, and we got the results from the previous slide were good, but when we did it on a sphere, we got this trace, which is exactly what we want to be looking for. It's sort of the minimum chi-squared or mean squared error across the sky. And for this, after about 50 calls to Shape, remember before it was maybe 400 to 1,000 calls to Shape, we got around sort of 20 degrees out from, which is reasonable considering we have like an uncertainty of around 10 degrees. And this is using passing an ellipsoid shape in. So I'm going to pass to Agata to talk about the next stage of our process.
Thank you. I'm going to be talking about the generation of training data for the neural network. So similar to last year, we tried to tackle the whole shape modeling process in one single step of just using the neural network, or at least creating good starting conditions for further shape modeling using the neural networks. But if you want to train a neural network, the computer scientists here will know that you need to show it what it's going to do. So you need to have a good data set from which it can learn the features of the system, and from which it can then try to interpret the data that's given. So we've created a synthetic data set to train our networks. So the input to the pipeline that creates the data set is a set of 3D shapes in the form of triangular meshes, and those shapes look like this. And also the different positions of the rotation pole, so the lambda and beta that can be searched for with the Bayesian optimization or with shape directly. There's this different sizes of the asteroid, and we used different asteroid orbits, making sure that they would correspond to real asteroid tracks that can be actually observed by radar. Also, the distribution of the periods and the sizes of the asteroids was tuned so that it would reflect the actual distribution of the asteroids in the near-Earth neighborhood. Now, the output of this pipeline is a data set that consists, first of all, of the asteroid shapes, but in a form that is easy to understand for the computer. And we have tried playing with two different formats. One of them is the 3D voxels, and the other format is the point clouds. So this is the voxel representation, this is the point clouds. And also we have the whole collection of metadata, and we have the synthetic Doppler delay images, which have added noise to make sure they look just like the real images look in real time, in real life. Now, last year, FDL team based on real asteroid shapes from existing databases, but those databases are quite limited. We have about 1,600 models that look more or less like this, and they don't really resemble real asteroids much. They reflect some properties of the asteroids, like general elongation, but they don't really have all the non-convex features like that the real asteroids have, like necks or craters or stuff. And we only have about 30 models like this known of asteroids from radar or spacecraft imaging. So we looked into generating random shapes. So we used software that generates asteroid shapes from spherical harmonics. And we can generate about 1,000 asteroids per hour right now using the IBM hardware provided by the FDL partners. So this is examples of the shapes, and this is examples of the synthetic images that we use to train our networks. And I'm going to pass it to Adam.
So we have all of this data now, and we need to do some training. So we tried lots of different sort of structures of networks, but before I get into it in a bit more detail, just touch on what was sort of done last year. So last year, we sort of learned that we can represent these asteroids, these voxels, so to speak, as a latent variable, like a vector or something like that. And we're basically going to try and build off of that. So we've been looking at generative models. So you can think of this as, well, we want to sample some latent space, some vector, which encodes information about general asteroids. And then what we want to do is we want to condition our network here, which we're just going to consider as a function with a lot of parameters, function approximator that takes in an input and gives us hopefully a good output. And we want to condition this network on our delay Doppler images and all of this other data that we've got in the tool set that we created in order to try and get the shape that we really want, an asteroid shape at the end. So I'll just take you quickly through some of the kind of architectures that we go through, and you can always talk to us at the end in more detail if you want to know. So something that we tried, a variational autoencoder, and the idea here is instead of going straight to this latent space here, the Z's that I've got up here, we want to go to this sort of stacked normal distribution defined by means and variances, draw from that, and then go through the process just similar to before and get back to the asteroid. So again, we're interested in this generative model side. So once we've learned all of this stuff, we want to just cut the beginning off, well, one example anyway, cut the beginning off and just put this generative model that we want to take all the data that we have observed, pass it through and get an asteroid. So that's the idea. We played around with other architectures, generative adversarial networks. We tried modifying the variational autoencoder, modifying the encoder part to change it a little bit. And other things that we're really keen to carry on working on is we don't really want to, as Agatha said earlier, we don't really necessarily want to just be working with voxels. I mean, this voxel is 32 by 32 by 32. Compare that with a point cloud, which is, we were looking at like 1,024 points. We'd much rather be working with that kind of thing. So these are kind of things to be thinking of going forward. I just mentioned graphs there as well, which was another thing we were looking into. So just pass it back to Data.
Yeah, so just before we finish, of course, once we have the results from the neural networks, we need to have some way of verifying it. And the way FDL 1.0 tackled this problem, and Shelly's smiling at me, was to directly compare the input shapes that produce the echoes and that we know produce the echoes with the output shapes. But that's not the way that astronomers traditionally do it, because we don't have the advantage of knowing the asteroid shape a priori. This is what we want to get out of the modeling, so we compare the input images with the output, and here we have a few examples of like how the input model looks like with the synthetic echo that we generated for it for the database, and this is compared to the shape that is a result of transforming the original mesh to voxels and back to mesh and creating synthetic echoes from that. So ideally, after we run our modeling with neural networks, we have methods to verify our results the way the astronomers usually do that. So in the end, we had a few bottlenecks in the general shape modeling procedure that we decided to tackle, and that we were quite successful in reducing by at least an order of magnitude. So the pre-processing stage of the data analysis is quite a tedious task, and anybody who's been doing astronomy knows that is the least favorite part of anything. So we managed to cut it from like a few days of clicking through images and making sure everything's right to a couple hours. Then the spin state search, which usually can take weeks. Can take up to a week, depending on how complicated the actual model is. Now requires like an order of magnitude less calls to shape, and it can be limited to like maybe a day or two. And finally, the final fit can be significantly reduced, because instead of like exploring a lot of dead ends, we can get quite close to the actual solution and just refine the model slightly. So what we want to do next is we want to publish those results. So yeah, we are intending to keep working on that and get those things out there. We want to make our code nicely wrapped up, commented and documented, and put out there for people to use. And also our methods don't have to be limited to be used by asteroid researchers. Grace here is an ocean engineer, and she thinks that it might be useful in modeling corals. The signal detection pipeline might be useful for the long period comets team for detecting meteors in images, who knows. And also we want to get the huge database that we have. We can essentially produce as many asteroids with voxels and Doppler delay images as we want. So we want to get it out there, and maybe somebody can tackle that and do it even faster than we did. So this was us. Thank you.
Thank you. Well done, guys. And, I'm sorry about that beeping noise. It's not the asteroid defense alarm. But hopefully we can get an AV person to come and help just during the Q&A, just to figure out what it is. Hoping. In the interest of time, I'm wondering, going to the panel, perhaps we see if there's anybody who's got something pressing who wants to kick off. Whilst you're thinking, I'd also like to introduce Saad Khan, who's joined from Uprising. Saad, do you want to stand up and just wave to the crowd? Thanks so much for joining. But is there anything, Victoria, do you want to kick off?
I do. I have one question. For, let's say, newly observed object, people are very interested. How many observations, or how much time how much observation do you need of that one object to feed it into your model?
So the networks are trained on 10 to 15 images. So ideally, we would love it to be like a live process. So as soon as we gather a data set, we can get an idea of the shape.
Yeah, sure. So we, the networks we've been training, as much data as possible is great, but what we did is we chunked the delayed Doppler images into like sets of 15 or sets of 10. But the way we did it, we could easily have lots of sets of images of the same asteroid, pass it in and do some sort of measure of uncertainty across an asteroid shape that comes out. So we're not limited in that sense. We're limited in the structure that we choose, but it doesn't. More data is better, I would say, for this kind of problem here. Yeah.
Okay, so I have a bit of a nitty-gritty question, which is your synthetic asteroids. I love that technique, and I know you said you added noise to them. However, I couldn't help but notice that your synthetic Doppler images looked a lot cleaner than what I'm used to seeing. So have you tried turning up the noise and?
So yeah, we've been experimenting with that a lot, and a huge chunk of our work was dedicated to make sure that this data set reflects the real data set, but there are certain limits into how deep you can get into that. Currently, we have ways to. So currently, we are. For example, for the delay resolution, we're making it as high as possible. That's the limit. So that's not very realistic. You don't always get that. The signal to noise ratio we select to be between 50 and 500, which is more or less typical when you actually want to do high resolution imaging and shape modeling. But it's not terribly difficult to make it like lower signal to noise ratio and get an even more realistic set.
Perhaps one more call, please. Yeah.
So this is an interesting project because you're building on the work from people last year. And so if the next group comes up next year and they're trying to build off of what you did, what advice would you give them in terms of what they should be trying to do and possible future directions of research?
Yeah, so that's a good question. We really benefited from working from what last year did. We didn't have to go and define the problem in the same way that a lot of the other teams had to do. And I think from the sort of, now we have this tool set to create lots and lots of data. We didn't really get a chance to truly exploit that. And I really think building on that would be a good starting point, and it'll be really useful for them. I also think the tool set can produce point clouds as well. We're looking at that, but we haven't really done much with that. And I think that would be a great thing to use. Also, like maybe someone else in the team can say something, but the pipeline we've been showing just parts of the pipeline that we chose to focus on. Last year they didn't do much. They didn't know too much about the need for masking. We were lucky enough to have two people who are experts in the asteroids in this area, and they were like, we would like to do it would be easier if we could do masking at the beginning and stuff. And these are things we didn't know about, and the team last year didn't know about. So there's plenty of more areas in this pipeline that need metadata. There's plenty of more areas in the pipeline to look at as well, so there's always things to do, and there's plenty to build on. So that's a good question. There's nice and fun things to do as well. So.
But yeah, we hope they'll be able to just pick up our software and continue with that.
Great. Well, let's give the team a round of applause. Thank you. Our next team is the Lunar Resources team. Of course, this team wouldn't be able to achieve what they've done without the help of Michael Bush and Shetty Rassi. And if you guys want to stand up and take a bow.